Okay, so I really love computer arithmetic. Seriously, I mean, I just love it. I mean, if I had to do one thing, I would do computer arithmetic. But one problem is, it's hard to advertise it, even in academic circles in Turkey, because they ask you, if you write a TÜBİTAK project, they ask you what's yaygın etki. Yaygın etki, normally they expect, oh, this is going to create employment for 1,000 people. No, it's not going to create employment for 1,000 people, because there are 1,000 people at most doing this in the world, okay? But you're going to be one of those 1,000 people. I mean, that's a lot of motivation. And one of them, or some of them, will be Turkish, right? I mean, this is really valuable stuff. This is really valuable stuff, but it's not going to create employment in hundreds or thousands, okay? Anyway, I don't know what the yaygın etki is, but it's definitely, it has an impact. So the very first thing that I would tell everyone, look, it's really such a nice thing, and it's really not complicated, but on the other hand, it really is a combination of smart techniques. So by computer arithmetic, I don't just mean the problems. I actually don't mean the problems, I mean the solutions. The solutions are clever. And I will tell you what I'm talking about with what we call Wallace tree. I forget his first name, but the last name is Wallace. He's a die-hard electronics guy. He published a paper, I think it's late 60s, possibly either early 70s or late 60s. And this guy is an electronics guy. I mean, in the paper, you see transistors. He thinks he invented a circuit. No, he did not invent a circuit. He invented some arithmetic. He invented an algorithm, actually. But since he was a die-hard electronics guy, and he was trying to design a multiplier circuit. The impact of what he did was really later realized by somebody called Luigi Dada. I mean, Dada, I'm pretty sure either he's a mathematician or he's an electronics guy, but he realized that this is nothing but math, what Wallace did, and he improved on what Wallace did. Luigi Dada, he died recently, and we sort of we stood up, and we had a moment of silence for him because he died. With one of my students, and he was also a research assistant here, although he was officially a student at Boğaziçi, Bilgida Yüce. He's at Virginia Tech now. With him, we went to Computer Arithmetic Symposium in Austin, Texas, in the US, and there we had a moment of silence for this guy. He died, he was 90-something. He had just died recently. He's one of the most famous computer arithmetic people in the world. And he's the most famous computer guy in Italy. He had his education, PhD, I believe, in the United States. Then he went to Italy. He became a famous person. He's the first guy to bring a computer to Italy. This is like after the Second World War or something. So what's the idea with Wallace? Wallace was trying to design a multiplier. I'm not talking about an analog multiplier. I'm talking about a regular digital multiplier. But let's look at the multiplication problem. What he really did wasn't really about multiplication. It was about summation. So Wallace was trying to design a fast multiplier. So then this brings the question of how do we do multiplication? So there is no requirement that a digital multiplication circuit will do the multiplication exactly the way we do it. But if you're going to come up with something new, you should always ask yourself, how would I do it manually, right? If it's something you already do manually, like let's say you're working on image processing, you have to solve an image processing problem, just ask yourself first, how do I do it? Because we're good in image processing, right? If you don't know where to start, ask yourself, how do I do it myself? So, step one, compute the partial products. So you may not be familiar with these terms, but this is what you really do, compute the partial products. And step two, sum the partial products. I'll show you. So product means the result of a multiplication. So you do little multiplications. You then add the results of those little multiplications. You get the result of the big multiplication. So let's give an example. Example in base 10. Let's say we're multiplying 123 with 422. So you multiply 123 by 2, 246. You get another 246. Then you get 492. Then you add them. 6, 10, 9, 11, this. So these are partial products. These are partial products. So partial product 1, 2, and 3. And this is their sum and the final product. I made a mistake. 246. 246. 480, 492, 6, 10, 9. We're recording it, so we should stick to one language. Okay, so no, actually he's right. He's right. He says in your algorithm you're missing the step of shifting. Okay? But if my definition of a partial, if my definition of partial product is this is partial product 1, partial product 2, partial product 3, then we don't have to shift anything. Okay? Anyway, so you get the idea. So the first partial product comes from multiplying the first multiplicand with the first digit of the second multiplicand. Second one comes from this, and the third one comes from this. So let's do a binary example. And it's not simply a base change. When you go to base 2, which is binary, there is a critical change. Let's even do the exact same thing in binary. 1, 2, 3 in binary. So there is 64, 32, 96, 16 is 112, 8, there is no 4, 1, 1. So if they were all ones, it would be 127 minus 4, 123. So this must be correct. The second number is 511 minus 90. Minus 90. Let's write 90. How do we write 90? 64. 16, which is 80. This. So 0, 0. And let's check 256 plus 128. 256, 128. Are you sure? And this is an odd number, you're right. Somehow I made a mistake. Then plus this, which is 32. Then this is 6 for 22. Okay. And let's do it like this. If you see two numbers multiplied, but one is shorter, one is longer, maybe you should really write it like this. Times this. And the partial products are what? The partial products are simply, you don't really have to do a multiplication, you can AND. Since it's 0 multiplication by 0 or 1, it's simply an AND, right? So you either write this as a partial product or you write zeros. So we're going to write the same thing. Like Emir said, shift it and write it. Then I'm going to skip, but let me write my zeros. Then 1, 1, 0, 1, 0, 0, 1, 1, 0. Yanlış mı yaptım ben ya? Yanlış yaptım. Okay. Oh, no, I'm correct. Okay. So I'm going this way. Then I have 4 of these. This, this, and this. 1, 1, 0, 0, 1, 0, 1, 1. 1, 1, 0, 0, 1, 0, 1, 1. 1, 1, 0, 0, 1, 0, 1, 1. Let's hope that we get the same result. 0, 1, 0, and we have a carry of 1. 0, and we have a carry of 1. 0, we have a carry of 1. This is 2, a carry of 2 now. 5, 1. I have a carry of 2. 5. I have a carry of 2. 6, I have a carry of 3. 5, I have a carry of 2. 0, I have a carry of 2. 1, I have a carry of 2. 0, I have a carry of 2. 0, I have a carry of 2. İnşallah doğrudur. Okay. English. Okay, so let's see if this amounts to the same number. So let's start. 2, 4, 8, 16, 32, 64, 128, 256, 512, Am I here? 1000, 2000, 4096. And this one is 8192. I think in terms of digits, we're missing something. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15, that should be 32,000 something. So I made a mistake. This is 2, 4, 8, 16, 32, 64, 128, 256, 512, 1000, 2000, 1000, 2000. No, 1000, 2000, 2048, 4000, 8000, 16,000. So this is 16 times 1024. And this is 32 times 1024. Does anybody have a calculator? You summed it up? Correct? Okay. I mean, he's pulling my leg. Mert, can you do it? Yes, I can do it. Really? Okay. Okay, so this is how we do it. Okay, so let's talk circuits now. Sinan, you have to sign the attendance sheet and write down what time you came. So design a digital circuit that does this. Design a digital circuit that does this in binary. But let's do it not for the particular example above, but for the multiplication of two 16-bit numbers. Okay? So, okay. And let's call those numbers this A 15 to 0 Verilog notation, B 15 to 0. Okay. So this may look like gibberish to you, but I'll explain what this is. Okay, so this is a good old AND gate. 1 bit, 1 bit, 1 bit. Good old AND gate. And this is actually the same as this. So number 1 to or number 15, number 14, number 13, number 0. So this is a stack of, or let's not call it stack, a pile of uh, 16 good old AND gates working in parallel and doing a bitwise, a 16-bit bitwise AND. Okay? So your multiplication that you do to produce the partial products is a multiplication of a 1-bit number with a 16-bit number, which can be done actually with a bitwise AND. You don't have to really do any sophisticated circuitry, because an AND is a 1-bit multiplication. Why can you do a multiplication with parallel ANDs? One AND does a multiplication of two 1-bit numbers. But you're not really multiplying one 1-bit number with a 1-bit number. You're multiplying a 1-bit number with a 16-bit number. But since you're multiplying a 16-bit number with a 1-bit number, there is no carry. That's why you can use parallel AND gates. There is no carry problem. Okay? If you were really multiplying, if you were doing in a different base, different radix, if we were multiplying a 2-bit number with a 16-bit number, then it would be a quite complex circuit. It wouldn't be simply AND gates. Then it would be recursive. We would have to solve the problem of multiplication to solve the problem of multiplication. But this is really not multiplication. This is something else. This is like, in a recursion, this is the termination condition. A lot of times, in a recursion, the termination condition hopefully becomes a much simpler problem. Okay? So these are my partial products. These are the partial products. Partial products. Now I have to sum these. I mean, so this is no big deal. This everybody knows. But what people still do not know is this. How the hell do I sum this? And in late 60s, this guy came up with a marvelous solution. Incredible. I mean, it's so simple. You tell yourself, God damn it, I mean, I could have thought about this. I mean, if I just lived 30, 40 years earlier, I would have been the one. Incredibly easy. As easy as zeros and ones, but I haven't told you the solution yet. And still a lot of people don't understand this. Because not too many people teach computer arithmetic. There are only two books, textbooks that are really used by people. One is by a professor called Israel Koren. He's really from Israel, but he lives in the States, University of Massachusetts, Amherst, 2 hours from Boston. And the other is on the West Coast, actually your university, Behruz Parhami, University of California, Santa Barbara. He's a Persian guy, but not of Muslim faith. He's a Baha'i. And actually, we're going to, so July 8th, we're going to, me, my wife, and unfortunately no student is coming. We're going to California. Computer Arithmetic Symposium is in Silicon Valley, and he's one of the speakers there, Behruz Parhami. Israel Koren will be there, and ours will be the first presentation, and that work is with Anil Bayram, who's at Dialog Semiconductor now, and Emre also contributed to that work. Okay. But that work is about multiplication. No, that work is about, yeah, I mean, we're working on so many different problems. It's about division, right? And constant division. Okay, so how do we do the summation? Do we do it the human way or a different way? Okay, so let's do it the human way. Let's do it the human way. So instead of going digit by digit, as you see, I really got confused. We could have done it this way. We could have really add these two first, right? We have to sum these up. Usually humans, okay, sometimes they do it this way, but we could also do it this way. Add these two, then add these two. I mean, doing this exactly the way I did, it would be really complicated because it's a slightly complicated algorithm. I have normally a carry, elde, is from one digit to the next, right? Here I have multiple carries. You get it? I have a carry of 4. I mean, I get 5, but I can only put the 5 as 1, 0, 1. I can only put the 1 on the right-hand side. Then 1, 0. So I have 5. I write down the 1. So I have a carry of 4, but since I move one digit, I have a carry of 2. It really gets complicated. Having a carry that carries over multiple digits, it's complicated. I'd rather do it this way. Add these two. If you're adding two binary numbers, you don't have a carry over multiple digits. Add these two, then add the result with this, add the result with this, add the result with this, add the result with this, add the result with this, right? And let's do it. But before I do it, I don't trust your camera. I'll take a picture of the board like I've been doing in the last few years without exception. But no, I mean, you haven't seen me lecture for the last few years. This is how I do it now. And this works pretty good. I have a new phone, that's why. My previous phone was really of bad quality. There's too much reflection. But anyway, still. So how should I? There's no way I can get rid of the reflection. You take it. But I mean, it will take you too long. You're going to look at all the adjustments. That's okay, man. No, it's okay. Although there is a reflection, it's fine. It's fine. Okay. We're still doing Wallace tree. You'll remember that. Okay, so the human way of doing it translate it to a circuit. Doing summation. So I call this summation, I don't call it addition. Addition is adding two numbers. This is something beyond that, right? So let's call these, actually, let's annotate the above picture. Let's call this partial product 0. Let's call this partial product 14. Let's call this partial product 13. By the way, I did not explain the notation here. This is Verilog notation. These are all curly braces, curly brace open, curly brace open, curly brace close, curly brace close. This is obviously a 1-bit number, bit 0 of the second multiplicand. And 16 means I duplicated 16 times. It's a fan out. One wire comes in, 16 copies of it go out. So the next one would be on the right-hand side, at the right input of the AND gate would be 16 copies of B1. It goes like this. This is 16 copies of B14, 16 copies of B15. And so basically, if this is 0, you're ANDing all bits of the upper number with zeros. Now, what comes out? 0 comes out. If this is 1, you're ANDing all 16 bits with 1. Same thing goes out. It's like a multiplexer, really. If you did a multiplexer, logic synthesis would optimize it out to this. It's either the number itself or 0. And this is the select. It's a 2-to-1 multiplexer, optimized. And these are, so if I was doing this with a multiplexer, I would have a 2-to-1 multiplexer that's 16 lanes, 16 bits, which is really 16 parallel 2-to-1 multiplexers. And this is 16 AND gates, regular AND gates in parallel, okay? So, here I have, now you could say, why do I need the, Xilinx does it for me, right? If you're doing a high-speed design, you may not achieve your clock frequency. And it's not like you're going to do, most of the time, your own multiplier. Sometimes you end up with a problem which looks like multiplication, but it's not exactly multiplication. It's possible. I mean, I'll show you later. Or you're doing a saturated multiplier, for example. You could do a regular multiplication, do like post-processing on it, and then either the circuit is too big, or a lot of times the circuit is too slow, and so on and so on. Okay? This is partial product 0. This is partial product 1. This is partial product 2. And this is partial product 15, but since we start from 0, this is really actually 16. And this is the sum, equal to the final product. Is this a detailed enough picture to show my summation circuit? No. Are two adders always the same? No. Depends on how many bits of a number they add. The first one is 16 and 16. Is that right? No, it's not right. But like Emir said, actually this guy is always, he's underrated. Yeah, I mean, he's really an incredible guy. He deserves more, 0.2. So like he said, this is shifted to the left. So if we want to treat this as a regular addition, we should really treat this as a 17-bit number. So this is really 17 bits. So if you add a 17-bit number with a 16-bit number, what's the result? No, it's actually 18. There could be an overflow. Yes, this is not the maximum possible 17-bit number. No, it's the 0th bit that's 0. This is the maximum value of this is 1 less than the maximum value of a 17-bit number. So anyway, believe it or not, this is 18 bits. Now this is, how many bits is this? This is also 18 bits. Not necessarily they are, okay, so normally we would say this is 19 bits. This is 19 bits. Is it 19 bits? I think it's 19 bits. It goes like that. So we started at 16 here. This is 18. Then after that, it will go 1 by 1. How many adders do we have? This is plus 1, plus 2, and I will have plus 15. After each one, it will increment by 1. But the first one, it incremented by 2. So this should be really 32 bits. Right? It should be really 32 bits. If you multiply, and what we're doing is, I haven't said that, we're doing the multiplication of two unsigned numbers. We're not getting into sign. It's complicated. We'll do it later. Not now. If you multiply two 16-bit unsigned numbers, it actually doesn't matter if they are signed or unsigned, I believe. If you multiply two n-digit numbers, you get a result of two n digits, right? 16 times 16 gives you 32. So this is not the same adder as this. This is a bigger adder. There are more gates in it. It takes more time and so on and so on. Okay. Then there comes the question of how do we do an addition? How do you do an addition? Again, you ask, if you have never done it, how would I do it as a human? How would I do it as a human? How do we do addition? Look, because of this, you should see it right there. I would never do a solve, at least a computer arithmetic problem, for a particular instance of the problem. Am I going to design this separately, none of them are the same. But if I can design it for n digits, n bits, and if I can write a generator, I push the button, I generate all of them. I design once, I use it multiple times. Okay? How do we design an adder? Adder sums two numbers. Okay, the human way. You should be familiar with this. Possibly most of you saw this even in your undergrad logic course. Let's call the two numbers we're adding A and B again, but obviously it's not the same A and B. Let's call them maybe X and Y. This is R for result, R0. Okay? So what's a half adder? Half adder is this. Half adder adds two 1-bit numbers. Two 1-bit numbers and gets a single 2-bit number. Full adder adds three 1-bit numbers and as a result gets a single 2-bit number. So if you can design these, you can cascade chain these to add any number of bits. So it's 16 of them, the first one being a half adder. The first one could be a full adder, but it's like the third input is 0, then you optimize it out to what we call a half adder. But although these are called adders, they are not really adders, they are 1-bit adders. I mean, it's a misnomer. It's really not an adder. An adder is really something that adds real numbers. Real numbers are multiple digits. These add only single-digit numbers. This is the equivalent of that AND. That AND does a particular type of multiplication. Only multiplies with 1 bit, right? An n-bit number. These only add 1-bit numbers. But by cascading these, although these add, so this is the most fundamental one. This is an optimized version of this one. It's the same as this, but the third input is a 0, right? So if you have a fundamental component that adds 3 1-bit numbers and gives you 1 2-bit number, then by cascading these, you can add numbers with any number of digits, any number of binary digits, right? So this one is actually, this one is really a circuit like this, right? Normally, okay, now let's stop for a brief moment. What are we trying to do? I'm trying to do a functional design, a design that does the job. But there are multiple ways of doing it. I'm trying to do a design that's really fast. What does fast mean? What does fast mean in the world of logic design? Man, how can less gate be fast, man? No, actually, this guy is also smart. Okay, he deserves bonus points. Smart guys like this, you have to really react to them first, but then think about it. Then you should insult them. Then you realize, I mean, man, I'm insulting him too much. No, then you realize you should not insult these people. He is trying to say this. Designs with fewer gates, less gates, they are fast. Right? That's not what he meant, but anyway, let's say that's what he meant. Yes, sometimes, but then there are some tricks in logic design which let you lower the number of gates and make your design also faster. Since there are fewer gates, there are fewer paths through these gates and they become faster. But after a while, exactly, we'll come to that. But after a while, you're done with simple tricks. Simple tricks lower the number of gates, make the number of gates less, also make the computation time less. But after you're done with simple tricks, you cannot make any more progress. The more sophisticated tricks to make circuits faster make the number of gates more. So it's like Heisenberg's uncertainty principle. Like, what's Heisenberg's uncertainty principle? I don't remember. That's another thing. It's a product and it's a constant. It's Planck's constant. If you lower one, the other goes up. Okay? A lot of things in engineering are like this. If you lower one performance criterion, if you make one better, lowering is usually better, the other becomes worse, goes up. Okay? So time and area, the number of gates, are normally inversely proportional. Inversely proportional. So where is that sound coming from? Okay. Okay. So tell me the speed of this circuit. But in the first place, what's the speed of a circuit? What do we mean by speed of a circuit? But there's no clock here. Tell me on this circuit. I mean, there's no clock here. No, that not necessarily. Okay, one by one. Let Aydın finish, then I'll let you go. Next. But then, I mean, you should define what speed is first. Then, I mean, once we know what speed is, then we can think about how we can estimate it or how we can measure it. But what's really speed? Görkem. No. Okay, Barlas. Barlas, go ahead. I mean, I promised you. I promised you. No, okay, Görkem then. Görkem. No, machine cycle also means something about clock. We don't have a clock. No cycles. English, man. I mean, we're international. We're recording international. We're recording for the whole world. Yes. No, yes, English. That assumes pipelining. Okay, again, good. But sophisticated subject. Okay, let's go back to them. Emir?
Let's go half-adder n time and full-adder 2n and we sum them up.
No, I'm not asking you how you can measure it. I'm asking you to define speed. What's the definition of quote-unquote speed of a circuit? Barlas? Barlas? Emir, your name is not Barlas. Barlas. This guy is a genius. No, I'm not talking about you. I'm talking about... Okay, so Barlas said it in a very nice way. The time, yes. Actually, he didn't define speed. He defines 1 over speed, latency. Exactly, we'll come to that. But so the kind of answer, the simple answer I would expect would be latency, although you don't have to call it latency. You could call it just like what he called it. He called it the time from the point you feed the inputs to the time result comes out. Computation time. Speed means, by speed I mean computation speed. Speed is opposite of time, right? The less time you take from one point to another, the higher your speed is, right? Speed is 1 over time. Clock frequency is 1 over clock period, right? So he defined time. That relates, as it relates to speed, and the time we're talking about, this is computing something, it's the computation time, it's the time from the time you input the inputs to the time you get the correct outputs. Very good. He deserves a mark, actually, 0.25. Okay. And that's what we call latency. A lot of times, what we care is not the latency, but the throughput. A lot of times, we use the same circuit to carry out the same computation over and over again on different inputs. And we basically ask this question: do I really have to finish one computation before I start another computation? No, you don't have to. If you start inserting flip-flops, when you do pipelining, you can really start a new computation, a new copy of the same computation before the first one ends, right? Then we're dealing with the time between inputs. What's the minimum amount of time that we have to wait until we can input a new set of inputs? That's cycle time. The speed equivalent of it would be throughput. Okay, but I'm going to here deal with latency only. So latency of this circuit, or any circuit, latency of And latency is computation time. Latency of any digital circuit is the critical path. Critical path. Critical path means really longest path. Longest path means if you think of the circuit as a graph, the longest path of the graph. And digital circuits can be thought of as directed graphs, where the connections, the wires have a direction. Okay? So all the full adders and half adders are on the critical path here. If I'm doing an n-bit adder, if you ignore the fact that this one is a half adder, it's n times full adder delay, right? If every full adder takes 1 nanosecond to compute, a 16-bit adder would take 16 nanoseconds. It's n minus 1 times full adder plus half adder delay. Let's suppose half adder delay is half the delay of full adder, then it's... You're right. N minus 2 times full adder plus half adder delay. You're right. So if this is half, for a 16-bit adder, this would be 14 and a half, right? Okay, then the question is this. Normally, most people assume this. So let's assume full adder doesn't take 1 nanosecond, but it takes 1 unit of time. And this takes 0.5 units of time. This is just an assumption, not necessarily this is always half this. So the delay of this guy is 14.5 U. And the delay of this guy, is it 14.5 U? Because this is not a 16-bit adder. This is really a 17-bit adder outputting an 18-bit number. So we should subtract always 1.5. This should be 15.5. 15.5 U. And this should be 16. Is it 16.5? No, 18. Yes, 16.5. This is 16.5 U. And it goes like that. This one here would be 17.5. And the last one takes what? The last one takes 31-bit here, 31-bit here. So 29.5 U. So this human circuit, very humanly designed circuit, what's the critical path of this whole circuit? How much computation time does this take? Okay, go ahead. Give it a try. So 1 point bonus. So as soon as I said 1 point bonus, he woke up. The question is this. We computed the computation time of a given adder. So the formula is n-bit adder computation time. Hang on, compute time is n minus 1.5 U. And I put it down on the bigger circuit, which does the summation. I'm asking you the computation time of the summation circuit. But the simple summation circuit, not Wallace's, the regular humans. 300. We could do Gauss's method, right? They all have 0.5. And how many of them do we have? We have 15 of them. 29 to 15. So 29 plus 15 is what? 44. And we have 15 of them. 44 times 15 is what? 660, but we have to take half of it. 330. 337.5. Is it what you said? Okay. Did he really say that? Okay. Did you use Gauss's method? Okay. No, but it's not the right answer. I gave you the bonus points, 0.4, for being able to add them up correctly. That's not the right answer. So the compute time of this circuit is not 337 and a half. Okay, so I raise it to 3 bonus points. Whoever is going to give me the right answer will get three bonus points, and I will give you the right to skip one more lecture. No, I'm just kidding. So maybe I give you the choice. Okay, should I give you 3 points or I give you another lecture to listen? Okay, what's the right answer? 3 bonus points, seriously. No. So assume wire delays are 0, yeah. We don't know what the wire delays will be. If you're doing it on an FPGA, obviously wire delays are important, but again, we don't know what they are. Maybe we can approach it experimentally, but again, we don't know what they are. We don't have cycles. This is a combinational circuit. No, okay, no. Engin? U? How is that possible, man? I mean, even a half adder is 0.5 U. No, but I'm not talking about pipelining, or I'm not talking about cycle time. I'm talking about the time from the point I input the inputs to the time the final product comes out.
9.5.
One by one. Go ahead.
9.5.
No.
+1.
Same? Same thing. No, actually, I don't know the answer. Let me compute the answer. Hang on. No.
But they should make each other to complete before they calculate this.
Okay, but you're missing one giant thing, all of you. All of you are blind.
Give us something.
You have the same blind spot.
Ah!
Okay, hang on. Let me compute it. Okay, I got it. What the hell are you doing? Oğlum misafirlerimiz var dışarıdan, yani yanlış anlayacaklar, tamam yani. We really like each other and we're not really too serious all the time, but then five bonus points. Seriously, okay, I'm not going to go above that, but 5 bonus points. So it seems like whoever is able to give me the right answer is really a genius, at least genius of the day. Like, no, there are no flip-flops. The definition is exactly the way you defined it. The time from the inputs to the correct output. 20, no. No, latency of AND gates, I'm just asking this circuit. I'm not asking the AND gate. No. No. You're close though. I mean, you're close just by luck, but I'll give you 0.1.
No luck, but I can explain.
Explain.
We take the first one,
Okay.
and the rest will continue, and I add the last one.
So how do you get 40?
15.5 plus
Plus?
29.5. What is that?
No. Okay, well, you'll really, okay, I give you a clue. I drop it down to 1 bonus point. I draw something like this. Okay, I drop it down to 0.75.
Hocam pipeline yok dediniz ama.
No, there is no pipeline. No. The longest path of this circuit is not the sum of the longest paths of the sub-circuits. If you have two graphs, if you chain two graphs, the longest path through the combined graph is not necessarily the sum of the, there is no longest path which goes through all the longest paths of all the subgraphs. The longest path of this guy, this is the second adder. The longest path of this guy enters here, comes out here. The longest path of this guy enters here, comes out here. For the longest path of this guy to be the sum of all the longest paths, you should be able to go here, then come back here. There is no such path. If you go through the longest path of this guy, you're not going through the longest path of this guy anymore. You're starting here. And if they were all the same size, each one would add only 1 U. But since the size of the adders grow by 1 bit, you add 2 U. You add 2 U here, you add 2 U here, you have 14 more adders, you add 28, 28 plus 15.5 is 43.5. A lot of people who do digital design, they have no idea. When they come up with an architectural design, they just add the delays. They come up with the computation time of the sub-circuits. They think the computation time of the bigger circuit is the sum of the computation time of the smaller circuits, which is not true. Because it's a 17-bit adder, you need 17. The very last one, let's see, 17. The very last one can be a half adder also, but I'm not really doing that optimization. So one number is 17 bits. The other is, the second partial product is 17 bits because it's shifted to the left by 1 bit. The first one is 16 bits, but the 16-bit one, I think of it as a 17-bit number by putting a 0 on the left-hand side. Okay? Okay. So this row of half adders and full adders, they are equivalent to the first adder. So this is like the +1, the first adder. So this is +1. This is +2. And this is +3. This was 16 bits by 16 bits multiplied, and I had 15 adders. This is 4 bits multiplied with 4 bits, and I have 3 adders, n minus 1. Makes sense, right? The very first one there adds two 17-bit numbers. I make the 16-bit number for partial product 0 a 17-bit number, putting a 0 on the left-hand side. So this makes, this adds, that adds a 17-bit number with a 16-bit number. This adds a 5-bit number with a 4-bit number. Okay? So what's the critical path? By adding all the critical paths, you assume that there is a path that goes like this. That goes through all the rows. There is no such path. The longest path is this. The longest path enters here. One, two, three, four, five, six, seven, 8. 4 bits by 4 bits is 8 bits. So critical path, longest path. Is equal to for F plus H plus 2F plus 2F. This is for the first one, this is for the second one, this is for the third one. All the subsequent ones will add another 2U delay. Okay? I mean, I'm not sure if you need more explanation. I mean, let's not go into other kind of twists and so on in the thought process. We're trying to, the computation time of a circuit is the longest path. Yes, I found the longest path of sub-circuits, but I want the longest path of the complete circuit. Not necessarily the longest path of a complete circuit, the longest path of a complete graph is the sum of the longest paths of the subgraphs. Because there may be no path that combines, that joins those subpaths, those smaller longest paths to each other. Okay? Let's try doing this the Wallace way. Okay? The Wallace way. Wallace says, I'm not going to really add, if I'm adding 16 partial products, he says, I'm not going to add the first two first, then the next one, then the next one, then the next one. He says, my job is not about adding so many 16-bit, 17-bit, 18-bit numbers. My job has to do with bits. It's sort of like the first solution I showed, but a much simpler version, and which results in a much simpler and much faster circuit. His observation is this. He says, let's say I want to add three 4-bit numbers. Let's say we want to add these. With the same thinking, I would have a circuit which is pretty similar to this. This is not necessarily coming from a multiplier or partial products. The key here is the summation circuit. He says, I want to add these, but I'm not going to add them. So this is what he does. He says, I'm adding 1, 1, 0. I can add these 3 bits with a full adder, and the result is 2, right? This is 2. And this would be a carry to here, right? He says, no, I'm not going to take it as a carry and add it with these bits on the next digit. He says, he says, yaz tahtaya. The Turkish slogan is yaz tahtaya. He says, I'm not going to write it here. I'm not going to write it here. I'm going to write it here. So these are regular carries that I would write here, but he's not going to treat them as regular carries. He's going to save the carries. So later on, they came up with modifications of this technique. One of them was Dada, and they called it carry save trees instead of Wallace tree. He says, I'm not treating it as a regular carry. I'm just going to remember it. Then add these 3. That's also 2. I'm going to write the carry on the next line. Same thing here. Write it on the next line. This is 3. Yes. Do we have an answer? No, we don't have an answer. But you know what he achieved? He transformed summation of 3 numbers into 2 numbers. He has a way now to reduce. So he didn't sum, but it's like recursion. He reduced the size of the summation problem. So if you can reduce summation of 3 numbers to 2 numbers, and for this you can use a regular adder. For this, use one of these, which is not the best idea, which is not the most state-of-the-art, but you can do that. So let's do that one, if you like. Okay. These are 2 numbers now. You add them up. So,
To find the first one, you add 3 numbers.
right. So normally, you would add these 2 numbers. You would use a circuit like this, which has a long critical path, to come up with a single number from these. Then you would add it with this to get the final result, right?
So
here, this thing can be done with a parallel circuit. Like when you're adding these single bits and getting this, in the meantime, in parallel, you can add these and get these guys. These are in parallel. Okay, actually, let's focus on this task. And let me show you the two, the regular approach and the Wallace approach. So the Wallace approach would be this. The Wallace approach would result in a circuit like this. Since we have very few bits here, Wallace approach may not help you in terms of timing. We'll see. Maybe it does, maybe a little, maybe it doesn't, but it doesn't make it worse. Okay. Actually, this one, we don't need it. The answer comes right out of here. Okay. No. So this is the circuit after Wallace's trick, and the longest path is F plus H plus 2F, which is 3F plus H. Maybe we could say 3.5 U. Let's do it the normal way versus the human way. So we would add the first two, which is this. Then we would have another one like this. Okay. Hang on. Let me finish this. Now you tell me. And the critical path is longest path four and a half. But as n becomes larger and larger, I mean the number of numbers becomes larger and larger, the number of bits becomes larger and larger. Basically, this guy's solution is and on top of it, you can make this use a fast adder here, so on and so on. I mean, as the numbers get larger and larger, the savings become larger and larger. Yes. Say it again. Right. You may be right. Let's see. You're right. So maybe then there is no savings in this case. Which one? Anlamadım. Niye? Yo. No. So it goes like this. Oh, I see what you're saying. You're right. Okay. And here, Barlas is right. I will need this. Okay. So, hang on. So this is 3. So this is 4. So this is 4.5. And so this is 5.5. I still save 1. Yes, Wallace. Yes. Okay.
O aşağıda gerçekten health adder'a ihtiyacınız var mı human making satırın en sağdakine? Onu bir tane sola shift etseniz 4 tane full adder yerine 3 full adder bir tane health adder kullanıp da en üstteki health adder'ın sonucunu direkt aşağı yazsanız human making öyle yaparız çünkü.
No, you still need, this is not coming from multiplication. I mean, I don't know if this is a 0. This is just regular summation. I mean, think of these as XX, any numbers, okay? This is the problem of adding, not partial products, not shifted numbers. This is a problem of, which I'm trying to solve here, is adding just aligned regular numbers, just regular summations. Like, for example, if you're doing convolution, you would end up like with a problem like this. Yes. Yani, in one of our funded projects, for example, we're working with floating point multipliers, floating point operations. And especially if you get into the floating point domain, you have so many options as an engineer. On top of it, Computer Arithmetic Symposium is all about floating point multiplication addition. And interestingly, floating point addition, for example, is more difficult than multiplication. Because you just multiply the mantissa, you add the exponents. However, if you're doing addition, you have to align them and so on and so on. So all these things, just addition, but floating point, it's a complicated matter. So, for example, in one of our work, we can at least beat Xilinx's own multiplier generator. In Xilinx, you say A star B, or instead, we generate a module for you, you instantiate it, we do it faster. By a series, I mean, substantial amount, okay? And if you have to meet your timing, you have to run at 200 megahertz, and otherwise you're not meeting it. This comes as a lifesaver, okay? So I believe everybody understands me now. Let me take a picture of the board again. Okay. So I'm going to try to capture a bigger picture of this problem. What are we able to achieve with? So I only showed you a glimpse of Wallace. I didn't really give you the bigger picture. I will give you the bigger picture also. Maybe I will give you the bigger picture of Wallace first. Okay. So what does Wallace get us? Actually, let's try to do, I'm not going to draw the circuit all the way. I'm going to try to describe it with higher level drawings. Let's figure out how we would do 16 by 16 multiplication with Wallace. So the summation, so I have the partial product generation here anyway. Partial product generation. This would go into summation, but then Wallace is about how I do the summation. So different names for Wallace. It's called a tree. It's really not a tree, but it's called a tree. Wallace tree is also called carry save tree, because the idea is about not putting the carries back into summation, but saving them. It's also called column compression tree, because as you go in columns, you deal with individual bits at individual positions. Column compression tree. This is the most modern name. And I will simply call it compression tree here. And so this summation here becomes, in the case of Wallace, so in the case of 16-bit multiplication, I have 16 partial products here. So I'm trying to sum 16 numbers. So with Wallace's trick, if I can reduce 3 numbers to 2 numbers, I can reduce 6 numbers to 4 numbers, for example. I can reduce 9 numbers to 6 numbers. 6 to 4, 9 to 6, right? I'll show you. So eventually I can reduce the summation to summation of 2 numbers, which is an addition, which can be solved with an adder. So how do I do that? Let me show you. So here, let me do it here. So initially I have, what do I have? I have 16-bit numbers, but they are like this. So to simplify the problem, I can put zeros and make them all the same number of bits. If I make all of them the same number of bits, they will end up being 32-bit numbers. 16 32-bit numbers. Does everybody agree with this? For example, you're multiplying two 4-bit numbers. I mean, this x doesn't mean multiplication. It means just any value, 0 or 1. The first partial product is this. The second one is this. The third one is this. The fourth one is this. You sum them. To simplify the problem, I will treat them as equal length numbers. So this is what I'm going to do. What are they? They are 4 7-bit numbers. So this is n. If it's n by n, this is 2n minus 1. n, 2n minus 1. Okay? This is not optimized, but gives you a easy look into the bigger picture, a simple look into the bigger picture. So I have 16 31-bit numbers. Look, so I made the numbers aligned just like this one. So if they are aligned like this, I can turn them into 3 of them. I can group them in groups of 3, and with parallel full adders, parallel, they are critical path. They are like an adder, but they are parallel. They are really not an adder. They are compressors. Okay? So 16 31-bit numbers with one layer of full adders. How much can I reduce to summation problem? To summation of how many numbers? Okay. 11. But yes, exactly. It will be 32 bits now. It will be 32 bits. Now 11, I can group them again in groups of 3. There are 3 groups. 3 times 3 will be 3 times 2, 6. There is an additional 2. I cannot compress them. They are by themselves. It's not a group of 3. So 3 times 3 becomes 3 times 2, 6. There is 2 more, 8. Is it going to be 33 bits? Is it going to be 33 bits? No, it will not be 33 bits. I know the leftmost bit will be 0 because the multiplication can be at most 32 bits. So this is still 32 bits. 8. 3, 3 becomes 2, 2, 4. 2, there is 2 more, it becomes 6. 6 is 3 plus 3 becomes 4. 4 becomes 3. 3 becomes 2. And you take these, you add, you get the result. Now, actually, I erased it. So my previous critical path, let's remember, longest path of human way was what? Okay, so 14 of these guys, 14 of them, 16.5 plus 2 times 14, 28, 44.5. Okay. So we're not going to save that much, but let's see how much we're going to save. We can save a lot by making the adder fast, but let's see how much we're going to save. 1, 2, 3, 4, 5, 6U. And the last adder is 32. So 31 and a half. U. 37 and a half. 44.5 versus 37 and a half, which is not bad. But the size of this circuit is not bigger than the size of this circuit. Usually, in logic circuit design, faster circuits are bigger. This is faster and smaller. This is a win-win situation. It's usually you win some, you lose some, or what they say, no pain, no gain. This is no pain, gain. Win-win, not win and lose, or lose and win. But like I said, I can always make the last adder, a fast adder, which is a whole subject by itself, a whole lecture by itself, which is even more sophisticated than this whole idea of Wallace trees. And the human way, this is the stupid human way. The smart human way would be the following. The smart human way would not be using a chain of adders. The smart way would be using a binary tree of adders. And using fast adders in each of them. And I will write it down. That would be, from a CS point of view, it would be log n squared complexity. And this is log n complexity. This is like 3 log n, and the other guy is log n squared. So if n is, for example, if you're talking about big numbers, 64 bits, long integer. Log n is 6. The smart human way would be 6 squared, would be about 36 levels. Wallace tree way would be 18, half. Twice fast. And area would not be bigger, it would be even smaller. The stupid human way, because in this case the human gets lucky, 64 it would be 128. Even more maybe. It would be maybe 190 or something. It would be really huge. I mean, as the number of bits goes up, it really goes like this. I mean, it doesn't go like that. It goes linear, but the other guy goes logarithmic. Okay? So with 16 bits and with a stupid adder at the end, we did not save much, but it's still not bad. This much savings in logic design without making the area bigger, it's like dream come true. This is, compared to this, 15% savings. So if you're running at 200 megahertz, or if you were running at 170 megahertz, and you're not meeting your timing, you're all of a sudden meeting your timing. Incredible. Nobody gives you extra 30 megahertz. It's not that cheap. Okay? Go ahead. Okay. So I should... did I draw anything on number 4? Anything extra? Possibly not. So let's think about it like this. I mean, let me show you the basic scenario of compression. Again. Then I will draw it at a higher level. So sometimes I say FA, sometimes I just simply say F. So don't get confused with that. So this logic block, its job is adding 3 1-bit numbers. And 3 1-bit numbers, if they are all ones, the result is 3. It can be expressed in 2 bits. So think of it like, so from 3 numbers, I'm able to get 1 number. I mean, from 3 numbers, I'm able to get 2 numbers. Compression. So if I have, so let me maybe draw it explicitly. If I had 6 numbers, the width of these numbers, the number of digits of these numbers, it really doesn't matter. If it's 44 bits instead of 4 bits, I would put 44 full headers right next to each other. But if these are more numbers, six numbers, so this is how I would draw it. I mean, I could draw 8 full headers right next to each other, but that's not going to be the ideal drawing. I would rather draw them like this. Because it's also important what position these full headers are. when you make a generator. So how am I going to draw them? Okay, hang on, let me try. Okay. So the guy in the back will produce 1 bit here, 1 bit in this position. The guy in the front will also do the same. 1 bit here, 1 bit here. So I will have 2 bits here in this position, and I will have 2 bits in this position. So the best way to, instead of my X's, people put like Behruz Parhami, they put dots, dot diagrams. They call them dot diagrams. But we have a way that, which is even better. Behruz Parhami coincidentally used it in his book, but nobody else does. And I have discovered it before I saw it in his book. Let me show it to you. So let's say we're adding 6 numbers. So I represent it like this. I have 6 bits here, 6 bits in this position, 6 bits in this position, 6 bits in this position. And I call this a B line, bit line, number of bits. Yes. Okay. We have tricks like that. I'll show you. Hang on. So since I have 2 groups of 3 here, I can put 2 full adders here. And this is called a cell line. 2 full adders. 2, 2, 2. Now here, how many bits do I have? And I call it a bit pile or a bit stack. So this is a bit stack of 6, 6, 6, 6. If you think of these like objects in a warehouse, I have a column of 6, a column of 6, a column of 6, a column of 6. Now after some processing, I reduce this to a different pile. This outputs 2 bits here, 2 bits here. This outputs 2 bits here, 2 bits here. So erase this. This is like a Pascal triangle. A Pascal triangle, if you remember, it's like lets you compute combinations of different numbers. And it's a recursive tree. It's a recursive pyramid. This is similar. The number here, let's write 2. The number here is this plus this, 4. The number here is this plus this, 4. So you add these, write it here. You add these, write it here. So this is also 4, and this is 2. Cell. I have one group of 3 here, so I have 1 cell, 1 full adder. I have 1 full adder here, 1 full adder here. So this method is not like this, it's more optimized because it's looking at every individual bit. It's not gonna, for example, put zeros into a full adder. It will use, instead it's gonna use fewer full adders. So this is cell. Now bit, this is 2. How many bits do I have in this position? How many bits? Do I have 1 bit here? 0 plus 1 is 1. No, I have 2 bits because I grouped 3 bits here. 1 is a bypass, so it's not really 4, I grouped the 3 and fed it into this, which gave me 1 bit here, 1 bit here. But that 1 bit here was not processed and it was bypassed. So this is 2. And this guy is 1 plus 1, and 1 comes from here, so this is 3. So it's like this. It's like this. 1 plus 1 plus 1, 3. 1 plus 2 is 3. So cells, again, 1, 1, 1. Bits, 2, 2. This is not the most optimized method. This is sort of like my method and my representation. 1, 2, 2, 1, and you're done. You really have 2 numbers here. This means I have XX, I have XX, I have X0, I have XX, I have XX, I have X0. At this point, I have 2 numbers, but the second number, these bits are guaranteed to be 0. And I'm just going to add these up. And how many levels do I have? How many levels? If I did it that way, let's do it that way. I have 6 4-bit numbers. 6 4-bit numbers. Then it goes to 4 5-bit numbers. And 6 4-bit numbers, the result will be a maximum of 7 bits. Then I will have 3 6 bits. Then I will have 2 7 bits. From 6 I went to 4. From 4 I went to 3. From 3 I went to 2. And in the last level I have 6 bits. It's even better than this method, because this method thinks that the adder is adding 2 7-bit numbers. I'm in fact adding 2 6-bit numbers. Okay? And we can use, like Emir said, we can use half adders. And this is how we use half adders. I put a half adder here. I put only 1. If I put a half adder here, I have 1 bit here, and I have 3 bits here. Since I have 3 bits here, I put a full adder cell here, 1. Then I have 1 bit here, 1 bit here, I have 2 bits here. And the advantage of this is, look. My adder is not a 6-bit adder, it's a 4-bit adder. From 6-bit adder, if I go down to 4-bit adder, it's faster and it's smaller. And what did I do? I added only 1 half adder, 1 full adder. Possibly I saved more area in my final adder. This is called final adder. And I made it faster. Write a program. Actually, this homework is for everybody. Beginner doesn't matter. I mean, this is really fundamental stuff. This is not the first thing you should be doing in logic design, but unfortunately, this is what this course is about, and this is something you can do. But I will give you, the beginners will have to do more work. I will give you at least one little extra homework. But you have to do this also. But some of these homeworks, I'll tell you you're exempt. Just do something else, and I'll tell you what something else is. Write a program in Perl or Python or C. Java is not accepted. C, C++. I'm talking about a regular program, man. I'm not talking about a design. I'm talking about a regular program. Input, the bit pile at the input, output, the number representation of Wallace tree, bonus if you have half adders in your tree. So whatever I did here, I showed you a particular instance of it. Basically, somehow you're going to generalize this in an algorithm and you're going to implement it. And at the command line, you write me a README. I'm not going to enforce a particular input style on you. You just tell me, or maybe, okay, I'll tell you. So you do this. At the prompt, so this should be, okay, Perl or Python, I'm sorry. So I don't want to compile this to my platform. I mean, I may be testing your programs on Linux. I may be testing them on Windows. I don't know. No, not Java. I don't want an executable. That's bytecode. Hopefully Java CC, Java whatever virtual machine would be able to. Perl or Python? Is Java really so portable? Okay, or Java. Okay, so at the prompt, in Java you cannot do it, right? I have to write Java whatever, the virtual. What's the virtual machine's name? No. Do I type Java here? I type Java. Okay, Java, Perl, Python, my program, and I will run it like this. 6, for example, 7, 8, 10. It should work with any number and any number of numbers and in double quotes. And it will print on standard output all these. And if you can also handle H's so that you reduce the number of levels of the tree, you get bonus, but you don't have to. But because of that, in some cases, if you're doing a multiplier, you will have so many extra levels. With half adders, you can really cut down the tree really to fewer levels. So 61 points overall. So if I give you, no, not this one, total. All these homeworks will be 61 points. If I give you one every week, 61 divided by 7, so this is like 8, 9 points, or I mean, at the max, let's say 10 points, at the minimum 5 points. Not necessarily all of them will be equal weight.